equations work. Right? So the way that we understood our discrete stochastic systems is we just looked at some basic cases, looked at analytical solutions, and saw how far we can extrapolate from the basic analytical solutions. Turned out that you could get a lot, right? You got the whole linear stability theory. You can understand how things go to infinity. That's a lot of information, right? Could we do the same for ODEs? So the simplest ODE is, well, the linear ODE, right? So we always start linear. And so the linear ODE is defined as u prime equals alpha u, right? Here I'm going to say that this is a scalar equation, but in the same way we can get this to be multidimensional. So how do you solve this equation? Right, let's actually do this out. Just everyone should kind of have this in their head, in their heart. This is the physics. Physics is right here. So let me point this out, that this is u prime equals alpha u. Now how do we solve this equation? Well, we can remember that u prime is equal to du dt. So this is the hacky way to solve it. You need to actually prove that this kind of notational thing works, but let me kind of just show you the idea. So let me divide by u and multiply by dt. Right, so if you don't allow yourself to be doing infinitesimal calculus, then that's not a real operation, but there are calculi in which you can show that this is a real operation. Now, okay, we have du divided by u equals alpha dt. How do you get the solution here? Well, I want to take the integral of both sides. And so, okay, now I take the integral of both sides. And what is the integral of du divided by u? Well, this is log of u. And then I have, well, what's the integral of alpha dt, where alpha is a constant? It's just alpha t, right? And this is all plus a constant. So I have a constant on both sides. I subtract a constant over. I have one constant, right? I want to isolate u. I have log of u. What do? Well, I take the exponent of both sides. So I want to do e to this guy. I want to do the e to the log of u. And e to the log of u is just equal to u, right? So there you go. Well, this doesn't look quite right yet. So what I want to use now is I want to use the property of e. So I want to say that, u equals e the alpha t, e to the alpha times t, times e to the c, right? That's how you do, when you add exponents, that means that you multiplied. Right, so e to the c is another constant, so let me define a new constant, which is just c0 that I put right here, right? I'm just using the commutative law of multiplication, and there you go. There's the solution to the linear ODE, right? This is the function of time. It's equal to an exponential in time. How do you get what c0 is? Well, if you do, for example, so let's say my initial condition is u of, t0 equals, well, for simplicity, let's make t0 equal to 0. Let's say u t0 equals u0. Then what we see is that u of 0 equals, plug it into the equation, c0 e to the alpha 0 equals c0, right? So c0 is the value that you get for u at time 0. If you had different initial conditions, you can see how the same methodology works out. So there you go. The solution to the linear ODE is an exponential. Let's contrast that for a second with the discrete dynamical system. So un plus 1 equals un, alpha un. This gave us the analytical solution that un plus 1, or un equals alpha to the n u, right? Or u0. So it's very similar. This one is growing exponentially in terms of n to the exponent. Our new equation is growing exponentially with t in the exponent. It's very similar, right? As it should be, because they're both doing a very similar thing where you're just saying, take the current value that you are and then multiply, use that value of your current spot to be your current rate for how much you grow, right? And so they're both growing. It just turns out that you grow a little bit faster if you're continuously always updating your rate, which should make sense because the more often you update your rate, well, the quicker you're going to be moving if you're always increasing your speed. Right, so there we go. And so if we have this analytical solution, it's very easy to start analyzing some of the behavior, right? So if the real part of alpha is greater than 0, right? So think if you have complex numbers, right? Remember that when you have complex numbers, you have to consider the fact that e to the alpha plus I beta equals sine of alpha plus I cosine beta. I might have actually just flipped that, but double check. All right, so you can write down. Oh wait, that's completely incorrect. This is you write this down as e to the alpha times e to the I beta, and so this is going to be e to the alpha beta beta, right? So really what the imaginary term is doing inside of an exponent is it's just giving you what the rotation is, and the real term is giving you the relative size, right? And so if you have imaginary terms inside of the linear ODE, this causes spirals. Whether are you going to be spiraling outwards or are you going to be spiraling inwards? Well, this is then dependent on the alpha term, right? This alpha term, well, is your current rate of change, is it positive or negative? Or are you going up or are you going down? Well, when alpha is positive, then you're going up. When alpha is negative, then you're going down. And we can see that from the analytical solution directly, right? And so if alpha is positive, if the real part of alpha is positive, then alpha, this term in the exponent keeps on increasing, and so u of t is going to go to infinity. When the real part of alpha is negative, right, then you have e to the minus alpha t, or e to the minus, or e to the negative number. The negative number is getting bigger. That approaches e to the 0, or that approaches e to the minus infinity, right, and e to the minus infinity is 0. So this makes u of t go to 0. Now what happens when the real part of alpha is precisely 0? Well, remember, go back to this this over here, right? So when you have e to the alpha precisely equal to 0, then that term is 1. And all that you have is you just have the cyclic part. And so you have a solution which is either constant or it's periodic. Right. Why could it be constant? Well, because if you have 0 for your imaginary part, then you're not moving in circles, right? So it's either constant or periodic. And so you can move this directly to multivariable systems as well. It's the same trick that we had when we were dealing with discrete dynamical systems. So what you do is you say the linear system is now u prime equals AU, where what we mean by AU is, right, the same thing that we did before. Right, so we do u1 prime equals a11 u1 plus a21 u2, and you say that u2 prime equals let me call this 1 2, a21 u1 plus a22 u2, which is equal to u prime equals AU, where A is this matrix which is A11, A12, A21, A22, right? How do you see this? Well, if you do this matrix vector multiplication, against the vector u1, u2, you'll get this equation out. So okay, that is that's nice and simple, right? It's very similar to what we did before. And now we do the same trick that we did before to understand how, these multidimensional systems worked. We don't know how to do multidimensional stuff, so we turn it back into the scalar case, right? So how do we turn it into the scalar case? Well, we take A, we diagonalize it. After we diagonalize it, we change our coordinates, and in this new coordinate system, we have a set of scalar ODEs. And then we solve each of the scalar ODEs, and it gives us the same behavior, right? And so then we have the same behavior where, once again, it's all based on the eigenvalues. If all of the eigenvalues are negative, then in every direction we're going to 0, and so therefore u of t goes to 0. If any single eigenvalue is positive, then along that axis you'll find that the solution will go to infinity, right? And there's a very nice picture that we can draw for this. Let me actually, I'll see if I can find that picture, and I'll post it at the end. But what you can do is you can actually you can define your ODE system as existing on the axis of the eigenvectors, and then you can the solution is actually going to fall to the given axes of the eigenvectors in the order in which how fast they are. How fast are they moving? Well, that's depending on the eigenvalues, right? So the things with faster eigenvalues will fall to their will either fall to their axis quicker, or they'll spin out to infinity faster. And then from there, you can just track, is it going to 0 or is it going to infinity, just by positive or negative of the eigenvalues. So with discrete dynamical systems, right, the geometric properties were understood by, the localization around any given point. The same is actually true for nonlinear differential equations. So if you let df du be the Jacobian of the system, right, the approximation to how this nonlinear f is working is you take the Jacobian of the current system, you multiply it to u, and that is your current derivative, right? And so this is a consequence known as the Hardman-Grubman theorem. A lot of these properties that you know of before, for example, is there going to be a steady state? Well, how would you define a steady state here? It's slightly different, right? So what is the equivalent definition of a steady state? Well, remember that in the case before, what you wanted to find was that f of u, for the dynamical system, that was f of un equals un plus 1. You wanted to find a point where f of u star equals u star, right? This would mean that if you keep on running this dynamics, you're going to stay at the same place. What is the same behavior in terms of an ordinary differential equation? Well, if you have u prime star equal to 0, then you never leave that spot, right? So in the same sense, derivatives being equal to 0 is the same idea as what we had as a steady state before, which is something you should start to understand from your homework, as there's two kinds of equations that have a lot of similarities, right? Fixed point problems and root finding problems have a ton of similarities, and in a sense, whenever everything to do with fixed point problems in the discrete case becomes a root finding problem in the continuous case. So when you have this behavior, it's the same thing as a steady state, right? So it's a state that you move to and you never leave again. Well, when you're around a steady state, how do you know what your behavior is going to be like? You can do the same analysis as before, right? It's actually no different, where you do u prime equals f of u pt. Well, how do you want to handle that? You approximate it near the system, df du, u prime, or u star times u, right? So this is the matrix vector multiplication between the Jacobian and the vector u. And so how do you know whether you're going to be going towards the initial the steady state or away from it? Well, you look at the eigenvalues of u, and if the eigenvalues of u are all negative, right? So now it's based off of negative because of the linear ODE. So if all the eigenvalues are negative, then the solution will go towards the steady state, Right, so this whole idea of linearization carries directly over to this case as well. This will be something that actually becomes important when we begin to talk about the stability of the ODE solver. So how do you actually numerically solve an ordinary differential equation? Well, the way that you numerically solve an ordinary differential equation, as hinted a few times, is that you turn it into a discrete equation. And so the simplest approximation, the Euler method, is you can understand it as replacing your infinitesimal quantity dt by a non-infinitesimal quantity delta t. And so you're just doing the approximation that du dt is the same as delta u over delta t for some non-infinitesimal quantity. Right? Since u prime, or since delta u is just the difference in u, right? You can write this out where you have delta t equals f of upt, which equals un plus 1 minus un, right? This is just expanding delta u. And now you just rearrange. So now you just rearrange this equation. And let me kind of put this over here since we're going to be doing a lot more math. There we go. So let me just do this derivation out. You have fraction du dt equals f of upt. And now what we want to do is we want to change this. This is an approximation, right? That we have delta u over delta t equals f of upt, which we then expand. So we do fraction un plus 1 minus un divided by delta t equals f of upt. Now we multiply by delta t and add un to both sides, and you get un plus 1 equals un plus delta t f of upt. Right, so this right here is called Euler's method. It's the simplest approximation. You cannot do anything simple or more coarse than this. And this right here, you can see that we've turned this into a discrete dynamical system, right? Where we have un gives you un plus 1. Now I missed a detail. All right, what's the detail that I missed? Well, what is this u, right? What should you do there? Well, the simplest thing is to say, well, if I need to know how to calculate this in order to calculate n plus 1, right? So let me make this be un. Right? You can actually make the other choice, and we're going to have to understand which of these choices is better in some sense. But let's also try to justify this in another way. Right, so what we want to do is, what we're trying to do with Euler's method is we're trying to figure out how to calculate u of t plus delta t. Right, so let's do a Taylor expansion around u of t. Right, so we have, Taylor expand around u of t. The first term is the constant term. The second term is, well, for expanding t plus delta t at the value t, right, then the first term here should be t plus delta t. Right, so this should be t plus delta t minus t, right, which is also written as delta t. So you expand delta t away, and what is the value that we expand by? Well, we put down the derivative, right? So the first term in the expansion is u prime, and then we do, delta t squared. What I mean by delta t squared is delta t squared, not delta of t squared, right? Delta t squared, and divided by 2, right? U double prime plus dot dot dot, right? So this is the Taylor expansion of this term at the point ut. Now what we do is we say, well, by the way that we define this equation, right? U prime equals f of upt. So if we use the relationship that defines the ODE itself, then u of t plus delta t equals u of t plus delta t, well, f of upt, and then we just say that everything else is junk. So math cal o of delta t squared, right? And so if we drop off this error term, there you go, there's Euler's method, right? So this is at u of t here. And so this is a formal justification for why you might want to choose un, right? The other method works just as well, right? So you can do the same thing where you say, I want to calculate u of t, right? If you want, you can do the opposite. I'm not going to do the whole derivation. You can say that u of t equals, derivation, or you then expand this around u of delta t, right? Dot, dot, dot. Right, so then you're going to do the term of minus delta t, right? Because now you're expanding u of t at u of delta t, so you have to make sure you get your signs right. But if you do the Taylor's expansion appropriately, what you'll get is the other version, right? So the key here is that there's not a single unique way to build a discrete dynamical system from a continuous equation, right? This equation works. This is Euler's method. The version where you do the Taylor series, Taylor series in the other order will give you this equation. Every single different way of discretizing will give you a different discrete dynamical system that represents the same ordinary differential equation, right? Oh, and just to showcase where the order of error comes in, right? So we had this math cal o of delta t squared here, right? Now, if we want to figure out what the order of the approximation is, what we want to do is we want to take this term minus this term, and then we divide by delta t, right? We divide by this delta t term, and so what we have left over is, how correct are we calculating the derivative? Well, the derivative is about f of upt plus o of delta t, right? Not delta t squared because we divide by delta t. And so this is why we call Euler's method a first order approximation, because the error that it gives you in this expansion, in this local expansion, is of delta t, right? So better methods would then probably try to have order that is a higher value of the exponent. Why would it be a higher value of the exponent? Well, because delta t is really small, right? So if it's 1 to 1/10, the Euler's method will have an error of 1/10, right? If delta t is 1/10, Euler's method has an error of around 1/10, right? That's not exact, but you get the point. If you were to square that, then with a delta t of 1/10, the error in your approximation would be 1/100th. And so higher orders of the term here actually means it's decreasing faster. So let's actually start to look at some higher order methods, right? This discretization is a little bit lengthy, so I'm not going to write it all by hand. But intuitively, right, we did intuitively the way that we are doing Euler's method, right, is we're basically saying that un plus 1 equals un plus delta t times text derivative, right? That's essentially what we're saying, right? The first order approximation for how you should move forward is you take your current derivative value, and then if you move forward by delta t by your derivative, right? So the derivative is du dt. You multiply by delta t, that tells you how much you moved, right? That tells you how much you moved in the delta t step. So you take your derivative, you multiply it by delta t, right? You take your speed, you multiply it by the amount of time. That's the amount of distance that was changed. So you then update your distance by how much your distance changed. That's essentially what Euler's formula is doing. Except the key here, the reason why it is not unique in how you write this down, is that you're doing delta t times derivative. And what is a good approximation to the derivative? Well, there is no single good approximation because f isn't constant, right? You're not driving at a constant speed. You're always changing your speed, and so there's no one value you can evaluate your derivative at, which is going to be perfect for all possible equations. Right? That is then the reason why there's an error introduced. So what this Euler's method is doing is saying, approximate what will happen and how you'll move in the future by assuming over the whole delta t that your derivative is constant and your derivative is the current speed that you're at now. So what happens if you're in a car and you're accelerating and you make this approximation? Well, if you're depending on your time steps, right? If your time steps are not too infinitesimal, then in any given time span, your approximation is a smaller derivative than the true derivative because you're assuming it's constant while it's always increasing, right? And so that means that Euler's method under constant acceleration is going to underestimate how far the car has gone. Implicit Euler's doing the other version, right? Where you say, use the derivative of the future to tell me how I'm going to be moving over this time span. But if you're always increasing, then, well, it's going to overestimate how far the car goes. And so what would be the best approximation? Your naive guess might be, just take the derivative in the middle, right? And that is where the next method comes from, right? Where you can say, well, instead of taking the derivative approximation at the current time or delta t in the future, why not just do delta t over 2, right? 1/2 of the time in the future. And so if you're to write that out, you can say that, my derivative approximation is, the derivative approximation that I want to do right here is the derivative approximation at the point utk1, right? Well, how would you actually calculate the derivative at 1/2? Use Euler's method, right? So you do something like, un plus 1/2 equals un plus delta t f of un pt, right? That gives you an approximation of un plus 1/2. And then your next step is you do un plus 1 equals un plus delta t. Wait, this is delta t over 2 because you're only doing a half step, right? Then you do a whole step of un plus 1/2 pt, right? So you do a half step with Euler's method, then you do a whole step with the derivative calculated by the approximation of Euler's method. This is different from doing 2 half steps, right? 2 half steps would have the equation where this would have a delta t over 2 as well, and this would be un plus 1/2, right? So this is distinctly different, calculating different values from doing 2 half steps. So why might you want to do this method? Well, let's actually write this in a different way because we're going to start building up towards a new type of methods. Let me actually fix the thing here. Sorry about that. Fix the lecture notes to make them easier to read. So if we take a look at the right here now, you should see that we can write this in another way where we say, for the first call to f, let's call this k1, right? And then the second call to f, right? So for this equation, right, we call f once, we calculate something, and then we call f again. So we can write this in another form, which we'll see is kind of a pattern later, that we can call our first call to f, just k1, and then we calculate the second call to f, which is just this whole line is stuck right here, and then this is evaluated at t plus 1/2. This is then what we call k2. Now our update equation is un plus 1 equals un plus delta t times k2, right? We'll see that this is actually a very consistent pattern in a lot of different methods very soon. So how can you how can you show what this equation, why would you use this method, right? Is using the 1/2 actually better? Turns out you can prove that using 1/2 is actually significantly better than just using Euler's method. So how you do that is, well, you write this down. If you plug everything back in, you just write this down, right? So this is un plus 1/2 fn, where fn is this value right here, right? So you're now layering your u's together, right? So now you do a two-dimensional Taylor expansion. So same thing that we did up here, except now you do a Taylor expansion of all these terms around just t itself, right? Remember that u is a function of t. Fn is going to be a function of t because u is a function of t and t itself. So you expand out this big term right here, this little boy, to be something like, well, I'm not going to read this whole thing out because it becomes a jumbled garbage. But here's a function of unpt, and here's a function of unpt, right? Where the one thing that you have to make sure you keep track of when you do this Taylor expansion is you have to make sure that, you have, when you have these mixed terms, you have tu and you have ut, and so you have to make sure to add them together. That's really the only trick there. So there's your multidimensional Taylor expansion. And now just do the Taylor series for this, right? So u of t plus delta t equals u sub n, u of t, right, plus delta t f of unpt, right? Where did this come from? Well, that's the same thing of just plugging in the derivative here. I just didn't do that extra step, right? And then you need to have all these second derivative values, right? But if it's the expansion of u in terms of, if you do the expansion of u in terms of t, well, then you can write it in terms of f, and then you have to expand f in terms of u and t. And so for the same reason, then you have to find out what all these different cross terms are, right? Well, you'll see that here that this method right here, this method where we expanded out our numerical method, it's calculating the same terms at the delta t squared as over here. So the error is actually in this delta t cubed term. It's missing some of these extra terms. Our numerical method only has 3 of the terms in the delta t cubed, whereas you're supposed to have 5 of them. And so it's not capturing all of the delta t cubed behavior. It's not capturing all of the third term of the Taylor expansion. And so this is u of t plus delta t minus u of t has some order t cubed behavior, right? What is the order of the approximation then? Well, we subtract this over, we divide by delta t, and if we do that, then we have the same thing like up here, except now we have plus o of delta t squared. And so this method is called, let me do that out, right? So you have a method which is u of t plus delta t equals u of t plus delta t f of upt, right? Plus something like math cal of o of delta t cubed, right? And so then when you move everything together, right, you subtract out, so fraction, you take this, you subtract u of t, you then divide by delta t, and how well are you approximating the true derivative? Well, is you're approximating the true derivative like that, plus, now we've divided by a delta t, so it's plus o of delta t squared, right? So this means that if you half your delta t, you get 1/4 of your error. You're getting more back than what you put in. So this leads to the form of the Runge-Kutta method, right? How does this read off? Well, you have k1 equals f at your first point, right? And then you use your k1 to calculate some value in the future that you use to calculate k2 at. Then you use k1 and k2 to calculate what your some value in the future, which you calculate k3 at. And you can keep on chaining this idea, right? Where you use your previous derivative values to calculate your next derivative values. And this is what we call a Runge-Kutta method. Specifically, in this form, it's an explicit Runge-Kutta method. So all Runge-Kutta methods are a class of methods which have this style. If you then do the same argument as before, right? So you take all of the steps of your equations, you smash them all together in the end, you get some f of f of f of f of f of f call, right? And you can do that Taylor expansion here and see what has to be true to match the terms. You can get an equation in terms of all of these coefficients that tells you what needs to be true in order to match the first two terms, to match the first three terms, and so on. Right? So then you can kind of, codify the science of finding a higher order term or a higher order method into finding coefficients that satisfy making these Taylor series match between the method and the Taylor series and the actual result. So if you do this for example for the fourth order, if you want to find out what needs to be true in order to match delta t squared, delta t cubed, delta t to the fourth power, well, what you get is just a set of order equations, right? You always need to have that your b's sum to 1. That is the first order condition, and really what it's just telling you is that, just like we wrote down here, right? We want to do un plus 1 equals un plus delta t times a derivative approximation. So this final equation really just is un plus 1 equals un plus delta t times some linear combination of the k's, where if this is going to be a derivative approximation, it should be a linear combination of the k's where you're doing some weighting where everything, where your weights are always adding to 1. Otherwise, you're going to get values come from nowhere. You won't have conservation of matter or anything. Your equation will become screwy. And so this right here, that all your b's have to equal 1, is the first order condition. It's the one that has to be satisfied for the first term of the Taylor expansion to end up being just f. The higher order terms are much more difficult to see. They're not as intuitive generally. There's a whole nice way that you can use something called rooted tree expansions to be able to derive what the higher order terms are. So you can derive that, you have 200 and something terms that are required in order to do the 7th order Runge-Kutta method or something like that. I don't remember the exact numbers. So you can then sit down and be like, these are the 200 equations I need to satisfy. Let's find the vectors of B, the matrix A, and the values that satisfy the order conditions. And there you go. Now you have a higher order method. So the first method of this form that was found was what we now call as the classic Runge-Kutta method. Some people just call it the Runge-Kutta method, or some people call it RK4, the fourth order Runge-Kutta method. It is the classic one. People don't tend to actually use it in good fast code, and we'll see why in a second. But it's very, you can use some physical intuition to kind of understand its derivation. So that's why it's kind of, it was the first one that was found. The fourth order Runge-Kutta method was actually found before this general form was understood, and it's actually what was abstracted to get you this form. So what is the fourth order method? Well, the first thing that you do is you evaluate the derivative at your current spot, and then you use that derivative to calculate a derivative halfway, and hopefully it's a better approximation, right? That's the idea we've been working with. So now K2 is a better approximation for the derivative over the whole time span. And, well, what if we have a better way of calculating the midpoint, because we now have a better derivative approximation. So now let's use K2 to calculate what the derivative would be at K3, or to be the derivative at the midpoint, right? So we have a derivative at the current spot to give us a derivative at the middle, and we use the derivative from the middle to give us a better derivative at the middle. We use the better derivative at the middle to tell us what the derivative at the future point should be, right, by stepping forward. And then we use those 4 derivative approximations. We just do a weighted average of them, where we say the 2 things at the middle have more weight than the 2 things at the end. And so we need that all the b's sum to 1. And so this approximation just chooses 1, 2, 2, 1 divided by 6, right? And there you go. Now you have this is a derivative approximation put together by 2 derivative approximations in the middle, 1 on both ends. You weight it so that way the ones in the middle have more weight. if you decide to go through all the arithmetic here, or heaven forbid, if you want to just, go directly to the Taylor series expansions and do, all the terms of the Taylor series expansion, what you'll find is that this satisfies the fourth order, all terms up to delta t to the fifth, right? And the delta t to the fifth term is the first one that's chopped off. And then the same analysis where you move everything over, divide by delta t to the delta t is where you get that the order of approximation goes as order of delta t to the fourth, right? So this is a classic method for how you can get a fourth order time stepping. Now let's actually look into whether a Runge-Kutta method is good, right? So these are all the same family of method, the same family for how you can discretize a differential equation. There's entirely different families that we're not going to look at right now, but these are all like the same way, right? So given methods that have the same structure, where you repeatedly do f calculations of this form, how do you know which one's good? What is good and what is bad, right? So one thing that you can look at is order, right? Because as the order increases, you're calculating more and more the Taylor series expansion correctly. That's good. But more rigorously, as you decrease delta t, the higher order method will decrease its error faster. Not only that, but the actual terms of the expansion are going to be much larger, right? So much smaller. So notice that, this term right here is growing like a factorial as you go further out. So, if you go to something like 10 factorial, if you have a 10th order method, 10 factorials, a really big number. And so you can kind of assume that even if delta t isn't 0, you have delta t to the 10th power divided by a really big number. And so whatever terms are left over have got to be small, right? So in general, you can kind of think of higher order is going to be a better approximation. But does that mean that a higher order method is always more efficient, right? So we need to start thinking about what efficiency means in this context, right? So if I want to, if I know I want to go from 0 to 1, right? My constraint is I want to get to 1 as fast as possible. So why don't I just use delta t? Why don't I just use delta t equal to 1? Well, you can, if you're okay with the amount of error that's associated with delta t equal 1, right? If you're not okay with that amount of error, then, or stability, as we'll see in a second, then you have to decrease your delta t, right? So this becomes a game. Like, each method has a delta t which gives you a different amount of error. What you want is the method that decreases error the fastest, because if it decreases error the fastest, then that means you can increase your delta t as much as possible and do less work to solve the equation to the tolerance that you wanted, right? So the reason to get a better method or a higher order method is not to decrease error. The reason to get the higher order method is to increase the delta t that you can get to have the same error as another method. Now, there's a trade-off that's going to be happening here, right? Because notice that in order to get a fourth order method, we did 5 evaluations of f. We kind of can assume that, f is where our whole dynamical system lives, right? Our whole differential equation, that whole code that we wrote down for, Einstein's equation, or not Einstein's equations, but Newton's equations, right? This whole code lives as the f call in our ordinary differential equation. So to a first approximation, most of the time is spent inside of that f call. So you can kind of count your efficiency of the method by counting how many f calls you do. So this fourth order method calculates f 5 times, while Euler's method calculates f, 1 time, right? Because you just use one f call here to tell you how you move in the future. So as you go to higher and higher order, you're using more f calculations to get less error. Did you actually gain something, right? This is not something that's directly clear without more empirical evidence, right? Because why not just do 4 more, why not just use delta t over 4 instead with Euler's method, instead of using RK4, which is going to use, delta t, but use 4 f calls per delta t, right? What is the difference between these two methods? And you might think that you have a thing going on here, right? That we derived that a second order method took 2 f calls, a fourth order method took 4 f calls, and so a five order method, you are correct, it takes 7 f calls, right? So once you hit above 4, you no longer have even numbers of f calls for the number of steps. You now need more f calls per steps. So you need 7 stages to be able to get your fifth order method, and then this starts to grow kind of exponentially. So, I mean, if it's going to take you like 80 function, I think it's like 27 function calls for the 7th order Werner method. Is using a 7th order method actually better than just using delta t over 27th and using Euler's method? Well, let's look at a few plots to understand what's actually going on. So actually, before we look at a few plots, so what makes a method good? The first thing that you can start to look at for a given method, right? So all things being equal, let's say you had 2 methods of the same order, right? Assuming that delta t is small enough, maybe that's a bad approximation, but assuming delta t is small enough, then the term to the next order, right? So if I have delta t to the nth order, delta t to the n plus 1 is orders of magnitude smaller than the other terms, right? Why would that be the case? Well, because remember, it's going to have a smaller factorial and it's going to have another power of delta t. So think about like if delta t is, if delta t is 100, right? The next term here will have a bunch of items times another, times another delta t. So excuse me. So let's say delta t was 1/100th, right? Then the next term here would be something with a bunch of terms times 1/100 times the next factorial size term. Right? So this is going to be exponentially smaller. This constant gets exponentially smaller. You do have more terms here, but they're higher derivative terms. And if your higher derivative terms kept on getting bigger, then your equation is going to infinity. So your higher derivative terms are getting smaller as well. And so you can kind of go, the terms that are further down in my expansion are smaller, right? So let's look at the second order method, right? The second order method, its error, throwing off the fourth order terms because those terms are going to be smaller, approximately. The error of our second order method is equal to the values of the third order, right? The values left over, the values that you got wrong. If we want to understand the error in our equation, it's not just O of delta t, right? We take this Taylor series expansion, the one that we calculate from the method, subtract it from the true Taylor series, right? And so the error is, well, this term cancels, this term cancels, this term cancels, right? That's why it's a second order method. This term and this term doesn't cancel. And what we're left with is some constant times a bunch of these terms. Right. So approximately these terms and times this constant is the size of our error. And so the first thing that you can do is you can ask the question of, what happens if I just take all the coefficients in front of all these terms, and let's say I want to find the method that takes 2 f evaluations, is second order, and has the smallest average coefficient in front of all the terms. Right? That's a well-defined mathematical problem. You can find the method that does that. I think that this midpoint method is actually, if I recall correctly, this is the one that does that in second order. In third order, you have Hume's method, which is, which does that to getting all the third terms correct, and it has the provably minimum value for all the fourth order terms that you can get from 3 function calls, right? So this is called optimizing the leading truncation error, where you're trying to find the method that decreases the coefficients in front the most by matching most of these terms, right? You're basically saying that I can, theoretically, with 2 function calls, I can only match the first 2 Taylor series expansion terms correctly, but I should at least try to find the method that matches the third one as good as possible, right? If I have, this choice of A's and B's in my Runge-Kutta method. So this is where truncation error optimization comes in. And the most widely used method available, so if you ever heard of Dupree, or this, in Python it's called Dupree, in Matlab it's called ODE45. This is the method, the Dorman-Prince fifth order Runge-Kutta method, which you will implement as part of your homework. It is a tableau where this is your A, this is your B, this is your C, right? Where you basically use this method where it says what your A should be inside of a matrix, right? What your C is going to be how much you move forward in time, and then this tells you how, and then the bottom row calculates how you do this combination, right? So here you calculate f at your current spot, and then a fifth of delta t forward, you calculate a new f, and then you use the previous two values of f where you add them together, and then you calculate f at 3/10 in the future, and then you calculate using the values that you did in the past. You sum them together in a specific way to calculate the derivative at 4/5. Then you use the last four values to calculate the derivative at 8/9, and then you calculate the derivative at delta t. You calculate the derivative at delta t, and then this gives you the value at y1. There's some niceties that are actually found in here as well. So one nicety is that you might notice that these two equations are exactly the same. Why is that the case? Well, this is something that we call first same as last, right? So if you calculate, if you make something such that the first is same as the last, then, right, the equation that you use to calculate this last f call, this u, is going to be the u that shows up in the next equation as f of u, which means you can reuse this f value. And so in some sense, if you calculate f on this value, you go to the next step and you have to calculate f of upt, well, then you can just, if you've already stored this value from before, you can reuse it. And so even though this method takes 7 function calls in theory, in practice it takes 6, right? Because you're just reusing one each of these steps. So this is, this shows you that there's a lot of optimization that be going on here, right? You're no longer just taking things as 1/4. You're saying, what is the theoretically best values, such that if I put the values and I sum in a very specific order, and I enforce that the last row here equals the row right here, right? And I make all of the order coefficients true, what would the coefficients be? And this is the method that they get out. And so this is the Dorman-Prince method. It's a fifth order method, and it is generally considered one, it's a highly efficient method. It's not the most efficient method, we'll see in a second, but it's a very efficient method on a large amount of equations, and so it's widely used for non-stiff ODEs. It's kind of like the go-to, and it's been that way since it came out in the 1980s. Why is there this extra row? Well, this is for adaptivity. We'll get to that later. So okay, so that's Tableau optimization. You can see though that since this was done in the 1980s, there probably can be some improvements that are done, right? So here they had to actually make an assumption that there was a 0 in order to come up with a solution for what all these optimal values would be. It turns out that removing this 0 can actually optimize the method a bit more. And so this was, I think it was 2011, 2013. Sideris created a new fifth order method, which actually has more optimal coefficients than the Dorman-Prince method. And this is the STIT5 method in the Julia ordinary differential equation library, right? And it gets theoretically better, lower error for the same time step because an approximation was removed to get better coefficient values. Right, so this game of optimizing coefficients is still going. In fact, I gave a talk at a conference for the stochastic differential equation case last week, where I was describing new methods that give very high stability, something we'll define in a sec, very high stability for stochastic differential equations according to some stochastic Runge-Kutta method. So people are still heavily working on how to optimize these tableaus. So let's actually look at some benchmarks to really start to understand how different Runge-Kutta methods start to interact in terms of efficiency. I'm going to leave off Euler's method because Euler's method is just so generally bad. But if you want to see how bad it is, you can look up why should you not use Euler's method. I'll put a link to it in the lecture notes. But I did a article a bit ago on what is the work precision of Euler's method against RK4 if you're curious, and on equations that have 4 derivatives defined, Euler's method is just not viable. Right. Why do I say on methods that have 4 orders defined? Well, implicitly what's happening when we are doing these higher ordered Runge-Kutta methods, we're requiring more and more regularity in our f function, right? Because we're using the fact that the second derivatives are not infinite in order to have a second order method. You have to have that the third derivatives are not infinite in order to have a third order method. So you're using more information about your equation to get higher order. And if those properties are true, you generally get a more efficient method to an extent, which we'll show right now. So let's actually start to look at some benchmarks. So this is what we call a work precision diagram. In numerical methods, which are dealing with continuous objects like ordinary differential equations, you always generally have to look at a work precision diagram because you have to understand how the error of the solution is changing with respect to its time, right? Because you never have an exact solution, right? So you can't just measure it and just say, this is how fast it runs. Every single method will have a different amount of error. And so the question is more, how long does it take to get this amount of error, right? How many f calls does it take to get to this amount of error? You want to decrease the amount of work it takes to get to a specific amount of error. And if you look at this equation, or if you look at this benchmark result from the SciML benchmarks, you'll notice that it's not too simple. But there are some clear properties that we can pull out of this. So DP5 is this Dorman Prince method. I say it's a fairly good method because people use it a lot, but in this plot you can see that, or in this test case where it's a 100-dimensional linear ODE, you can see that the DP5 method does not do as well, but only in the case where order is low, or where you want low error, right? When you're okay with higher amounts of error, this trend is actually a lot steeper. And so if you're okay with higher amounts of error, then the lower order method does fine. Well, why is that the case? Well, remember, if you have delta t equals to 1/2, then delta t squared equals 1/4. And so if your delta t is very small, then the amount at which having higher order decreases your error is more. And how do you get less error in an adaptive time stepping method? Well, you'd have smaller delta t's, right? So essentially, as you go to the left on this axis, the adaptive methods, right, they're taking different delta t's every single step, but they're generally having smaller dt's. And when your dt's are generally smaller, that means that the efficiency of a higher order method has a better chance of paying off, right? Your delta t is smaller, and so your asymptotic analysis around delta t equals 0 starts to make more sense. And so one trend that you see in this is that high order methods tend to do better as you want lower error. So it's a user tolerance question. If the user wants a tolerance of 10 to the minus 3, you'll have a different recommended method than if they want a tolerance of 10 to the minus 8, right? If you want 3 digits correct, a lower order method like a 5th order method is good. If you want 10 digits correct, then you might need to use a 7th order, 8th order, 9th order method to do it efficiently. And that's one thing that you can suss out of this plot. Another thing is that methods of the same order are not created equal, right? So here, for example, you have Vern 8 versus Vern 8 versus DP8. So DP8 is a 1980s method created by Dorman and Prince. It is their 8th order method. It's one of the most popular 8th order methods. The Werner method is, I think it's 2017. It's a new optimization of the 8th order coefficients. And you can see that it can cause a pretty substantial performance difference, even though they're both methods that take the same number of function calls. It's just differences in the coefficients in the table that they choose. And so, optimizing your tableau can make a pretty significant difference. and the choice of order is dependent on the error tolerance that you want for your solution. So those are two factors that can be read off from one plot. Now, an interesting thing that we can also look at is, like a different dimension, is what does the effect of implementation tend to have, right? Because we've been talking so much about code performance, what does code performance end up doing here, right? So here we can look at, the Fortran method from ODE interface. This is the do-pre-5 method. It's the classic Hare Fortran method. The blue line is the new differential equations method, and the orange line is a method that is not the hyper-optimized version in the library. So the library implementation of differential equations.jl is doing a few extra features. It's basically doing what we did in the course, plus one little trick, which it's left off because it's detailed. And so what this kind of shows you is that, using a lot of just performance enhancements about has the same order of magnitude difference, about one order magnitude, as what would happen as the difference between RK4 and the difference between RK4 and the fifth order method, right? So RK4, the reason why it's not generally used is because it's not it has very nice coefficients. The reason why it has not very nice coefficients is because these coefficients weren't optimized. So it generally doesn't tend to be competitive. It's the one that you write down just because you can memorize it, but it's not the one that you ever use. So here, for example, is Dorman Prince method, this optimized tableau, versus the Sideris method, which I mentioned is the new version that gets rid of this assumption in the derivation and has slightly better coefficients. How well do these two methods compare? Well, in this equation, DP5 does a little bit better for a little bit of it, but then for most of it, Sideris is doing a little bit better. We found that on average, it's actually, the truncation error coefficient decreased by about 20%. If you average over a bunch of different ODE solves, you see about a 20% time difference. It kind of lines up nicely with the theory. What this shows you is that, if someone has already optimized the coefficients fairly well, there's not very much more you can do, at least for lower orders. For lower orders, there's only a few coefficients to find. For higher order methods, there's hundreds of coefficients to come up with, and it's still anybody's game for coming up with the best method. So how can we get a difference from Fortran here, right? Like, Fortran is actually optimized. It's not one of these very slow languages. So how do we get this difference from Fortran here? Well, one of the main reasons is because all of this is reliant on the cost of fcalls, right? And this is actually a very interesting thing to point out, right? So your ODE solver, right? What you pass to the ODE solver is the actual function that you want to calculate. So you're always passing this function. And so what the Julia library is able to do, because it is JIT compiled, is it's able to JIT compile this function call into the ODE solver library itself to be able to decrease the runtime it takes to solve the ODE. So you cannot do that if you ahead of time compile your ODE solver, right? Because if you ahead of time compile that ODE solver, then the ODE solver is already compiled to just say, I'm going to do a function call to whatever function pointer you give me. And if that's the case, it cannot compile per each ODE to opt to do extra interprocedural optimizations. So this is actually one funny case where JIT compiled languages can actually have a performance advantage over ahead of time compiled languages. So C++ and C, Fortran are not like the true gods of performance, which you might think. There are ways that JIT compilation can actually improve performance, and it's something interesting to kind of think about and try to use if you have a JIT compiler. Right? We've actually mentioned another case where this shows up. So function barriers are a case where you're making use of the JIT compile properties to be able to then enhance the performance of a downstream call. And there's a few other cases like that show up. So here is a very nice post about Scala, which what is shown is that if you try to do generic functions, right, like we defined about having functions that auto specialize between integers, float 64, and all that, you cannot necessarily always do that well in a ahead of time compiled language. And so you have to define all your specializations, and whatever you don't define a specialization on, you get a very big performance hit, right? So that's another case where JIT compile kind of starts to have a play in the way that you write your mathematical code. A third way, actually a very funny result, but the fastest way to call C code is not from C, but from a JIT compiled language, because it can actually compile away some of the call that is required to the C API itself. And so there's this very nice C API or CFFI, so C foreign function interface timings, which show that JIT compiled languages like Lua JIT and Julia are the two things that can actually call C faster than C itself when you have this C binary. So that's just kind of like I want to just kind of point out that, here we start to get this interaction between the computational science and the method, right? Where we can start to see that, JIT compiling your F calls directly into an ODE solver that has optimized coefficients can improve the performance of your overall solution. How much that matters depends on whether the function call itself is relatively large in consideration to the amount of work being done in that function, which, remember, a function call is 10 to 100 cycles. And so are you going to be doing more than 10 to 100 cycles within your F call? You start having, it's problem dependent, but you can start to understand all this to know when it's going to matter and when it's not going to matter. So the other performance difference that is being shown is due to the method, right? And so yeah, well, I guess we did go over that. So just to kind of clean up the story here, you're going to ask, well, what is the difference from Matlab or Python, right? Because here the real interesting thing is you're defining your F. You define F in the language that you're using. So if you're using one of these slower languages, then writing that function call inside of the interpreted language will probably have a pretty large performance hit. And if you do this this benchmarking between different languages, you see exactly that, where you can get this 50x to 100x performance difference due to these factors of basically the interpreter getting in the way. All right, so your whole homework one was to figure out how to write a discrete dynamical systems code such that you could get something about this fast. And remember that you probably had to look at things like, well, I had to specialize my function, had to make sure my types were stable. If I didn't, I was off by 10x. If I didn't specialize this other thing, I got 50x off, right? If you don't do all that, which is essentially what happens in a interpreted language, then you have about 2 orders of magnitude performance penalty, and that's what we actually see in practice. Right, so that's optimization of Runge-Kutta methods. It is both due to the method, right, which is due to optimizing the truncation coefficients, and then also at the very end of it, it just becomes a discrete dynamical system. So all of those techniques that we went over before are crucial to make sure that this is an efficient method. So now let's go into the stability of the method, because that's one of the other key factors for understanding whether a method is good or applicable, right? So simply having the truncation error does not imply convergence of the method, right? So simply in the case of that meme, right? So the disconnect is that the errors might not dissipate in the future. Let me kind of go through an example to really explain what that means, right? So to understand how or whether the equation will be calculating the right thing, let's look specifically at the linear ODE. Why do we do that? Well, because on the linear ODE, we know the analytical solution. So let's apply the numerical method to the linear ODE and see if we get something that resembles the analytical solution. So take Euler's method, right? It's un plus 1 equals un plus delta t times a derivative approximation at the current state, un, right? So we take this and let's plug in the linear ODE. When you plug in the linear ODE, you get un plus 1 equals un plus delta t times alpha times un. So now let's let z equals delta t times alpha. We'll find out why we define that in a second. And so we get the following. Un plus 1 equals un plus z un, which equals 1 plus z un. Right? Now this is a discrete dynamical system. This is a This is a linear ODE. For what values of z does the discrete dynamical system give you the same asymptotic behavior as the linear dynamical system? Well, we went over the stability of the linear dynamical system, right? If alpha is less than 0, then you should have that if alpha is less than 0, then you decrease to 0 over time, right? So let's only look at that case, right? The alpha greater than 0 case, your approximation blows up to infinity. So it's not as interesting. So when alpha is less than 0, you should have that the solution of the discretized ODE is going to 0, correct? All right. When alpha is less than 0, then z is less than 0. So what this is saying is that when z is less than 0, the true solution is going to 0. So this system right here, un plus 1 equals 1 plus z un, which is Euler's method on this equation, it should be going to 0 if we're calculating the correct thing, right? Does it go to 0? Well, we know how to do stability analysis, right? Our stability analysis says that, when the norm of this coefficient is less than 1, then this linear discrete dynamical system will go to 0, right? Let me write down that logic. So u prime equals alpha u, right, is the linear ODE. If alpha is less than 0, then u of t goes to 0. If alpha is less than 0, then we want Euler's approximation to have u sub n goes to 0, right? Because that means it's doing the right thing. So if alpha is less than 0, then z is less than 0. And now Euler's method is un, right? This is Euler's method where we now defined one term, right? So this is, now Euler's method is un plus z, un, which equals 1 plus z, un, right? This is Euler's method. Euler's method will have u sub n go to 0 if the norm of 1 plus z is less than 1. Why is this the case? Well, I mean, this is what this is what we showed with the discrete dynamical systems, right? We showed that in order for this thing to be going to 0, because the analytical solution is un plus 1 equals 1 plus z to the n u0, right? Because we showed that this was the case, then we need to have that the norm is less than 1 for the norm of the solution to be decreasing, right? And there you go. So this tells you that only when, right? So here, let me write down the definition. So remember that z equals delta t, alpha delta t. And so what this means is that only when for 1 plus delta t times alpha is less than 1, that the Euler discretization has the same general asymptotic behavior as the true continuous system. Right, only when that's true. Now alpha, right, that is your ODE. That comes from your problem, right? If your problem is to, this is a linear ODE. So if your problem was to solve this linear ODE, right, alpha is given to you, which means that you can only find, that you can only use a delta t that is as big as will let this still be true. right? So, if you're going to 0, then alpha is negative, and so that means your delta t is positive, but how big of a positive number it can be is completely dependent on what your alpha is, right? And there's a limit. So if alpha equals 1, then your delta t cannot be bigger than 1, right? Well, if your alpha equals -1, then your delta t cannot be bigger than 2. Right? Why is that the case? Well, let's let alpha equal to 1, right? And now in this case, if we let delta t equal to 2, then we get vert 1 or -1, because I want it to be going to 0, sorry. So 1 minus, -1, or 1 plus -1 times 2, which is this is directly equal to 1 minus 2 vert, which equals 1, right? And so you can see that if I made delta t any bigger, then this is no longer going to be satisfying the condition. And so if we think about alpha, alpha can generally be a complex number. Why would we think of alpha as a complex number? Well, because we want to apply this to any possible ODE. So when we apply this to any possible ODE, what we do is we say, I linearize my dynamical system around my current point. Around my current point, I have a linear matrix that is the Jacobian, right? I diagonalize my Jacobian to find the eigenvalues. The largest eigenvalue is the value that I'm going to look at, because the largest eigenvalue tells me whether I have anything exploding to infinity. So now let alpha be the largest eigenvalue of my linearization of my system at my current point. At this current point, the maximum delta t that I can use for Euler's method on this problem is given by, well, delta t has to equal 1 over alpha, or 1 over alpha plus 1. Yeah, I mean, it just has to satisfy this equation, right? And so that is why we want to do this as with alpha complex, because even with real Jacobians, you can have a complex eigenvalue, right? For example, the matrix 0, 0, 1, 1 has complex eigenvalues, right? And so even if you're looking at real systems, you can have complex eigenvalues, and all these kind of spirals that you see, they're due to the complex eigenvalues of the Jacobian, right? So what this picture is showing is that this is a picture of the possible, this is the picture of the possible z's which satisfy this equation. And basically you can say, if z lives in this unit circle, right? So if alpha times delta t lives in this unit circle, then you're stable. If you're outside of this circle, then you have this blow up behavior. And what tends to happen here is that when you're outside of the circle, you'll take one of these steps that jumps over 0. Right, so another way of looking at this is that this constraint is your step should never give you something where you go beyond 0. When you step over 0, then you suddenly have this equation where you have a negative where you didn't, and so it starts to give this amplifying behavior, right? Where you step over 0, but then now you have a negative, and so it's going to send you back over to this side. But now, if you're doing that same step, well, your derivative is going to be larger, because your derivative is equal to alpha times u. And so if your derivative is larger, now you're going to step over 0 more, right? Then that means you have a bigger negative derivative, and you jump over more, and you just start spiraling out of control. So this is a very good signature of you chose a delta t such that your method's unstable, right? You'll have this spiraling behavior, and you can understand it by looking at this linear equation. Yeah, so if you choose a delta t such that alpha delta t does not live in the unit circle, then you will see your numerical solution do this, which is completely incorrect. And so that means that you want to satisfy the stability condition in order for your discretization to even make sense, right? So when you're thinking about error, this is the error of my approximation if I'm satisfying the stability condition. If I'm not satisfying the stability condition, if delta t is sufficiently large, then my error is essentially going to go to infinity. Right? So the stability condition is necessary for having a good discretization. And so what this shows you is that these explicit methods, or at least these explicit Runge-Kutta methods, have strong bounds on the maximal size of the delta t, which is directly related to the size of the maximum eigenvalue of the linearization of your ODE at the current point. Yeah, I think, yeah, so I kind of went over this part. So this is really just saying that, yeah, the way to understand this linear stability condition in practice is that you linearize your dynamical system, any nonlinear one. You look at the maximum eigenvalue, that is what you can consider alpha to be. And so you need to be changing your delta t such that you're always making sure that the stability condition is satisfied. Yeah, sorry. So this image is showing the stability region of the second order method that we derived and the Runge-Kutta fourth order method. And you can see that there is a difference between them, right? So the Euler method is, remember, it's the shifted unit circle, right? It's just the equation that is given by, right? So it's the equation given by 1 plus alpha t, or 1 plus z, and norm is less than 1, which is just the shifted unit circle. The shifted unit circle. And so that's inside of the stability region for the second order method, which is inside the stability region for the fourth order method. Which means that your stability is actually much larger for these higher order methods, and so you can take larger time steps. Are they more efficient? Well, remember, this is dependent on a few factors like what is the error that you're actually looking for. If you're looking for less error, then it become more efficient to use a higher order method. If you are okay with higher tolerances, then using a lower. If you're okay with higher tolerances, then using a lower order method, like a fourth order method or fifth order method, is okay. Generally, it's usually never more efficient to go to below a third order method. Going below a fifth order method is fairly rare. So okay, so that's stability of these explicit Runge-Kutta methods. The way that you calculate these is the same way. You take the equation that you're looking for, this linear ODE, you stick that linear ODE into the differential equation's discretization, and then you just get an equation for what the update is. It'll be a discrete dynamical system in terms of, this previous term equals something time to the next term, right? And that gives you your stability condition, and that stability condition tells you what the stability region is. Now let's go to implicit methods, right? Because there's this other story that kind of popped up, right? So there was this other story of un plus 1 equals u sub n plus delta t f of u n plus 1 pt, right? There was this other derivative approximation that we could have did. And so in this case, if you do the stability calculation, right? So if we let f of u pt equals alpha u, right? This is what we do with stability condition. We say we want to calculate what happens for our numerical method on the linear ODE. So let's assume we have the linear ODE. Then the method is un plus 1 equals u sub n plus delta t alpha un plus 1. Right? Why un plus 1? Because it's f of u. It turns out that you always get an alpha times delta t, so you just redefine this as z. And now you have something different, right? So you have 1 minus z un plus 1 equals u sub n. Or another way of writing this is that un plus 1 equals the fraction 1 over 1 minus z un, right? So what we need is that we need vert fraction 1 minus z. We need this to be less than 1 in norm, right? Well, what is this? This is the opposite of the shifted unit circle in the other direction, which means for any of these values of delta t, then you have something that will be going to 0, which means that for any value, it doesn't matter what value of alpha you chose or what value of delta t you chose, right? For any negative value of alpha, for any delta t that you choose, the asymptotic solution of implicit Euler, like we're doing this method, it will go to 0, which means that for any of the equations where it truly goes to 0, you have the correct behavior in the end. That is a pretty nice property, right? Because it means that you don't need to worry about delta t. It's always correct. This kind of method is always correct in terms of delta t. We'll show that that's not completely the case. Your homework actually just showed that it's not always the case. So there are some extra details there. But in theory, this method right here can choose whatever delta t it needs, and it will always be stable. So that might be something that is a better method, right? What's the difficulty with it? Well, we have to solve an implicit equation because we don't know what un plus 1 is, so we can't calculate f until we know un plus 1. So we're going to have to do some kind of Newton's method to figure out un plus 1 from these kinds of steps. But if we could do a Newton's method, this kind of equation will not have a delta t restriction. So will that pay off, right? Will doing a Newton's method to calculate un plus 1, will that actually be better than just using one of these methods with a step size that's small enough? It completely depends on the equation. So there are some equations where it doesn't matter. There are some equations where it does matter. Equations where it does matter are called stiff equations. When it doesn't exist, it's called non-stiff. So this stiffness is related to fast slow phenomena, or having a fast time scale or a high frequency mixed with a low frequency. Why is that the case? Well, this is, given our discussion of Runge-Kutta methods, this should be a very informative plot, right? So let's say our true solution looks like something that, this very beautiful plot. You have this just kind of like you're bouncing around, and you have, in general, what's going on is the blue line. But you have a fast system that is causing this bouncing around as you have that general curve. What does that remind you of? It reminds you of these. It should remind you of some of these equations, like these chemical kinetic ones, where you had some very fast behavior mixed with slow behavior. Right? And on these equations, right? Think about what happens if you do Euler's method, right? Euler's method with a large delta t. Here, if I calculate the derivative and I truly get the correct derivative, right? If I have exactly the right value at this point, and I just calculate the derivative and I use Euler's method, and I say, I'm going to step forward by delta t by using the true derivative right here. You will go from this point, delta t, all the way up to here. And get something completely incorrect. Right? Why is that the case? Well, because the true derivative right here is not necessarily the derivative of the integral of this location, right? In some sense, this derivative averaged over all the time points inside of here is not large. It is actually close to 0. And so by calculating the derivative at one point and then stepping forward, you will be stepping off the solution. These larger Runge-Kutta method, or these higher order Runge-Kutta methods, instead of doing their first step to delta t, they do a step to delta t over 2, so they could do a little bit better, right? But you can kind of understand from this picture that if you're always going to be taking a derivative calculation and then stepping forward, anytime that you have a fast time scale that's kind of jiggling around the slow time scale, it has the ability to throw you off. And so this is really like the feature of stiffness, right? Like this fast time scale can really throw off your calculation if you are trying to extrapolate. So if you don't want to be thrown off your rhythm, right, then what you want to do is you want to kind of like find some way to average over the whole time scale. And that is essentially what these implicit methods are doing, right? Because you have to know the value in the future. How do you get the value in the future? Well, you're using some Newton's method to try to like figure out, what would be the approximate value now and in the future. And in some sense, it's averaging all these different values to give you this average derivative that is like the derivative of the and basically finds the derivative of the light blue curve here, and then it steps forward along the light blue curve. So it's still only a first order method, but it's a method that is not prone to these instabilities due to larger time steps. but it has a different cost, right? Instead of just being f-calls, now you have to do an entire Newton's method. So is that going to be worth it? Well, it completely depends on the equation. So I think this is where we'll end this lecture. That is the basics of discretizing ordinary differential equations. Now we're going to look into stiff equations, right? So in your homework, what you're going to do is you're going to get you're going to get some practice discretizing using the Dorman-Prince method. Once you understand the Dorman-Prince method well, this is like the standard explicit Runge-Kutta method. You'll feel like a star of explicit methods, right? And it turns it into this discrete dynamical system. Now the next thing is to really look at these implicit equations and ask, how do you do implicit equations well, right? Since a lot of these physical phenomena are stiff, right? In fact, most people would say, most hard equations that you run into, most of the equations that people are interested in scientific disciplines are stiff equations. How do you handle these stiff equations appropriately or efficiently, right? Well, you need to use these implicit methods in order to not have this time-step restriction. But how do you actually then do the Newton's method fast? How does the Newton's method interfere with the stability equations? Well, from your homework 1, you should know that using fixed point iteration is not as stable as using a full quasi-Newton, right? Relaxation of your Newton will increase your stability. So you have to think about the stability of the Newton solvent here, along with the stability of the method, and this will be the next topic in this course. How essentially is going to start overlapping with automatic differentiation for how do you do this calculation efficiently. Once we go through that will start getting us into automatic differentiation, which will start pulling us towards adjoint equations and how to do neural ordinary differential equations and parameter estimation of ODEs. So let's get through the stiff ODE solvers next, and then we'll be right at the spot to do neural ordinary differential equations.